So greetings and welcome, Ian. It's fantastic to have you on the podcast. I've been really looking forward to speaking to you.
Thank you. It's a pleasure to be here.
Now, one thing I like to do with all of my guests is to learn something about their origin story. So in your case, what did you study as an undergrad? And was it inevitable you'd end up in academia and in science?
Well, of course, that's a great question. So I can say it's quite a surprise that I became a physicist. I grew up in a high-rise council estate in working class East London. And every summer, my parents took me and my sister to the coast, not far from London. But when I got there, I would see at night the incredible beauty of the night sky, something you can't really see in London because of the light pollution. And when I was about 8, I got back to school after the summer holiday, and there was a competition at the school. The teacher said, make a poster about your summer. And I made one about the night sky. And what was interesting was that it was a competition. And so all the kids in the class had to vote what was the best poster. And they voted mine. And the prize for winning was that everyone in the class would make a poster just like that one, that is about the night sky. So some people made stuff about Venus, let's say, or another planet, or the galaxy. And then we got to put them all over the corridors in this small elementary school, primary school, in Walthamstow. And this had quite an effect on the school. And it also had the advantage that it made me quite popular. So this sort of got me started. And then, like most kids, I had a chemistry set. I read all the books in the library about astronomy and then about other subjects. And when I was reading a chemistry book, it was a very old and boring chemistry book. I didn't understand most of it. But early on, it talked about how the arrangement of electrons around an atom is the reason, one of the reasons for chemistry. And I realized that this arrangement of the electrons was due to physics because it noted that in the book, this is coming from physics. I didn't understand what physics was, but I now knew that it had something to do with the arrangement of electrons. And when you realize that, you begin to realize that, and then you explore that a bit further, you see how powerful physics is for explaining so many other things. And so that got me really interested. And then there was a guy on TV. And you may have heard of this guy. He was an astronomer. The program is called The Sky at Night, longest running TV program possibly on the planet. It today features my colleague Chris Lintott, but back when I was a kid, there was a guy called Patrick Moore who was an amazingly charismatic and eccentric person. He used to say, all you young people listening to me out there, remember, if you want to do astronomy, you must first start with a physics degree. So it so happened that then I went to the local university, Queen Mary, which is not only just down the road from Walthamstow, a few miles. It's actually around the corner from where my grandmother was born, within the sound of bells, many years earlier. And there I took courses in physics and mathematics. And the ones I enjoyed the most were the ones that were the most fundamental. And for physics, that became particle physics. And I thought that that would be a very interesting profession to follow if I was good enough. And people thought I was good enough. So I was given a place at Edinburgh University to take a PhD. And that led me to going to CERN within about 6 months of getting to Edinburgh, after a very interesting experience, having some tutorials from Peter Higgs, and then starting my career there.
And just going back to the personal side of things, I understand that you have a hearing challenge.
That's right. That's right.
So can you talk a bit more about that and how that's affected
sure.
your work? Because I understand it's quite serious.
That's correct. So I have no hearing. So what happened was after I went to the United States in '86, my wife and I, my late girlfriend, we got married in 1988. So 2 years after I was there. And then shortly after that happened, I had a strange pain in my kidney. And it was diagnosed. The doctor checked it out and said you have a kidney infection. And you do the usual things where you have sulfur drugs and things like that. But it didn't get better, it got worse. And so there was some more investigative work done at the local hospital at Cornell. And what they discovered was that I had a rapidly developing and dividing white blood cells all throughout my body. And this was a huge shock to everybody. Nobody knew what it was, but they did know it was extremely serious. And so thanks to actions taken by my colleagues at Cornell, it was possible to have me moved to the Cornell University Medical College in New York City. And the head of lymphoma, because of my age, I was in my 20s, So I had lymphoma at Cornell. I was put in charge of the case because lymphoma is a very common form of cancer in men of that age. But it turned out it wasn't lymphoma, but it was leukemia, acute myelogenous leukemia, which is more common in children than in adults. But it can, on the extreme edge of that distribution of age, pick up people that were my age. And the treatment for that was industrial strength chemotherapy. And that wipes out your immune system. And then I caught pneumonia, went into a coma. I was in a coma for 6 weeks. And when I came out of the coma, I still had my hearing, but I had been, to keep me alive without an immune system, I had to receive a large dose of medically necessary ototoxic antibiotics. And these, subsequently, 7 months after I got out of the hospital, removed my hearing completely by destroying the hair cells, which are the electrical transducers in the cochlea that pass the stimuli and sound and the pressure waves that pass through our body and into our cochlea, into electricity, and then on up in the auditory nerve to the brain. And so I lost them, and they don't grow back in mammals. And so the net result is you now have no hearing whatsoever. So that was a big shock. And I had to read. And my career, probably if I'd been in some fields, it would have changed a lot. But in physics, what matters is ideas. What ideas do you have? What things do you have to tell your colleagues? What will stimulate them to think in different ways? And it became clear that it didn't matter that I was deaf. Nobody cared. The point was I can go to the chalkboard, I can write down ideas, write down equations, and we could discuss them. And it's true, it was harder for me to understand, but people were very kind and they would write things down on a piece of paper if I could not understand them. And so my career continued to flourish. I won national prizes for a young scientist, the National Young Investigator Award at NSF. And the year I won it, 1992, only 2 people in the US won that prize in particle physics. The other was Lisa Randall, who's a well-known physicist at Harvard. And this kind of thing gives you independence. It gives you some funding to do your own thing, to hire your own postdocs and students. And I continued to work on the experiment at Cornell.
But when I'm speaking to you now, I mean, I'm speaking to you and you're listening to me and you're speaking back. So how can you hear me now?
Oh, well, so if I was still completely deaf, I would be reading, and I would probably ask you to have to speak very slowly. But what happened was that about 2002, I'd had ideas along with some colleagues for a brand new experiment at Cornell, and we'd just been funded for it. And they elected me the leader of the experiment, despite the fact that I had no hearing, which first underscores that being deaf, you can be a leader. But then it was one of my executive assistants back at Purdue, which was the university that paid my salary and gave me my start in my career, which Purdue is in the south of Chicago. It's a fantastic engineering school. She said, I've read an article about cochlear implants, and they seem to go a lot better. Why don't you find out more? And so I had a conversation with a colleague of Fermilab, and he told me that, and the reason I had it is because I'd heard he had a connection to cochlear implants himself, and the connection was his brother, or brother-in-law. And so I got to talk to the brother-in-law of this friend about cochlear implants. And this person told me that the device had changed his life. So I decided to learn more. And then around 2003, I was selected for an implantation at a very famous center for implants in the United States, the Raleigh Hospital for Children in Indianapolis, which implants people from around the world. And this restored my hearing. It took some time, it's quite a long story, but the net result was that it gives you back your humanity. It enabled me to hear my wife's voice for the first time in 12 years. That was the period of my deafness, and it hadn't changed. And the second thing was I got to hear my daughter's voice for the very first time because she was born after I became deaf. And there are no words in the English language to describe how remarkable that is. And my experience is similar to many other people that have an implant. Today, about 1 million people on the planet, roughly speaking, have an implant. However, there's probably 100 million or more that are either born profoundly deaf or lose their hearing in such a way that hearing aids don't help because of the damage to the hair cells, which mean no matter how loud the sound is made by the hearing aid, the sound doesn't get through to the auditory nerve, and hence there's no stimuli in the brain. And so it's a life-transforming technology, and it was the first neuroprosthesis to actually restore a neural function. So it's a truly remarkable device, and I highly recommend them to anyone that has the misfortune to lose their hearing or be born without one.
I mean, that's quite a remarkable story at the individual and personal level, but also testament to physics and science, actually, that it's the nature of the subject or the domain that allows ideas to stand above everything else. Now, I did want to ask a question about your experience at different universities. Obviously, you've studied in the US, you've studied in the UK, you now head up physics at Oxford.
That's right.
What's the approach at Oxford to physics? I mean, what makes, presumably you would have had a choice to be located to run any department or be associated with any department, but why Oxford?
Yeah, that's a good question. So after the discovery of the Higgs boson, there was a lot of interest for many of my colleagues and myself from other universities that were very well known, both in the US and the UK. And one starts to think about potentially moving, even though we were very, very happy, both in the US and at Purdue University, which is where actually home was, which is south of Chicago. And so when you start to think about these things and you look at the resources and capabilities and ambitions of universities, then a few universities stand out. And Oxford stood out for me because, first of all, as you know, it's one of the handful of universities that could claim to be one of the best in the world. That's not based on, of course, partly it's based on reputation in the past. But when I went to visit, what I discovered was that it was great today too. That there are remarkable breadth of truly talented and ambitious people here, and that they span a huge range of the subject, more so than almost any other physics department in the world. These people are not just experts in their own subdisciplines of physics, but that when you put it all together, what you see is that Oxford is covering all the major areas that matter from the arcane. For example, in particle physics, my own subject, it has what I think was believed to be, certainly in the US at the time, probably the best particle physics group at any university in the world, was in Oxford. So that would be a good reason to go. But there were other reasons too. It was also a spectacular university for astrophysics, another example of the arcane. And then at the other end of the spectrum, they were leading on things like quantum computing, they were leading on climate, they were leading on sustainability, for example, whatever it takes, solar cell, energy generation. And they were a center for quantum computing in the country, in fact, and they continue to be so. And these things are all very important. And there was also the ambition there to build a new building that would be the quietest building in Europe, by which I mean most isolated from the environment. And at the time, that intrigued me because the ambition to do that, it's very difficult to build a building. And the physics department said, we're going to build it. Now, it was an expensive building, and there was a lot of help from the university and a lot of help from private donors, but they did build it. And it hadn't been built when I got there, but they had a department describe the building like it was in front of us. And I thought, that's in building where I might one day be able to do an interesting experiment. And so that was another draw. So it was the ambition and the quality of the people and the proximity to CERN as well.
Now, you mentioned some topics, and this is topics that touch everybody, including our audience. Climate change. When it comes to climate change, there's obviously a huge interest in this area. There's a big impact on societies and the world and so on. From a scientific perspective, from a physics department perspective, I mean, what's the big question you're trying to answer? What is the cutting edge thing right now that you're working on in physics?
Right, but that's of course a very good question. So I want to start by saying that one of the things that's different about Oxford, you're quite right about the breadth and diversity. One of the things that's different is that climate physics itself you don't find that in physics departments in general. As you know, only meet climate scientists, very wise though they are, they're in other departments, they're not in physics. And what distinguishes our approach to physics of climate is that we start from that. We write down the differential equations that describe the atmosphere, and then we solve them. And that approach is very foundational. And so it tends to give you a different sense of how things work, why they work, that you might not have if you were not trained in physics. And so I think that is the beginning of what's different about us. So it's just the way that we think about it. Thinking like a physicist is a real thing. And we think like physicists. So that's where it all begins. As you know, what we're focused on is trying to understand the existential threat that climate, because it's changing, has on our society and how we can ameliorate that. That really underpins our work. And so I can say a bit more about that if you like.
Yeah, I mean, one thing obviously is climate models. I mean,
Yeah.
How do you simulate all of this? Because to me, it seems like financial markets. So financial markets are very, very, very difficult to model because you have humans interacting with each other, and that's a very tough problem. So you reduce it, but then there's a massive loss in terms of what you can predict. I imagine climate modeling. I mean, you have clouds to deal with, the precipitation, water. I mean, there's so many different factors.
That's right.
How do you go about modeling things like that? I understand there's the CM the coupled model intercomparison project and the sort of projects on simulation. But presumably this is where physics comes to the fore, I imagine.
Well, I mean, yes, I mean, it does, but then the physicists develop the basic equations that go into the models and make the predictions. And with large enough computing, high performance computing, and also the use of artificial intelligence as well, you can actually make remarkable predictions that seem to be able to, for example, demonstrate that the extreme weather heat wave we had in the Pacific Northwest in 2021, I think it was, or 22, and also Storm Eunice in the UK, and the incredible destructive power of those, you can directly link to climate change in ways that before you couldn't, because of the power of the ability to simulate the world today and run the models with and without changes in temperature. In other words, without the CO2 that's capturing that heat and driving the temperature of the Earth to dangerously high levels. And so that wasn't possible earlier on. It was possible to say, everyone's noticed climate's changing, but getting the models to tell you, yes, with a fair degree of precision, yes, it's not something that was possible to do before. It's just much of that work has happened.
And when there's talk about let's try to reduce emissions to mitigate temperature increases in the next 20, 30, 100 years, and then it will have XYZ impact, is that a approach? Is that something that's simplified for the benefit of the public to understand, or is that realistic to sort of look that far out, 50 years hence from now?
I think it starts with not so much a simplification, but in trying to explain these ideas, people have often misunderstood them completely. I've seen politicians, for example, talking about the importance of Britain achieving net zero. But some of them seem to think that what that means is that the things that produce so much of the heating, whether it is fossil fuels or whether it is fertilizer or concrete or steel, all these things have to be produced to produce a lot of CO2 and other gases that are a problem. If that's just all done abroad, then everything's imported, that Britain would achieve net zero. But that's a rather awful way to think about it. It's a misleading way to think about it, because we're talking about the planet being net zero, not one country. And I think that's dangerous. So I think there's been even when things are said clearly, they're not always understood. And so that's the biggest example I've seen is people taking this here, especially prominent people, and thinking that it's just for the country to solve in some way rather than for the world to solve. And that's really worrying. But the evidence of the temperature changes are extremely well documented and directly linked to the amount of carbon dioxide in the atmosphere. And if you look at the world before the Industrial Revolution and then today, and you see the dramatic increases in temperature that have gone up, you see the graphs. There's no doubt that this is happening, and we can model that.
Yeah. And this is probably more so in the US than in Europe. There are people who challenge the science around this all, saying, okay, it's if you look at sort of a long enough span of history, we have ice ages, we have temperature changes. This is just
Absolutely.
Within that distribution. And so what are we worrying about? And so instead, it's an alarmist talk by scientists on this topic. What do you say to that?
Well, I say it, and I find, incidentally, before I answer that, let me say that when I first taught climate change, it was as part of this astrophysics course at Purdue in the 1990s. And having grown up in the UK, I was less aware of the political sensitivity around climate change. And so when I first started discussing in class, the very, very bright students that were taking this class, hyper-selected students, fell into two camps. One group were absolutely, yes, this is very serious. And the other group where this was all a fiction. And the two groups broke down by which party they happened to be supporting. And I wasn't prepared for that. But what that did do, though, was it helps you answer more crisply what the effects are and why it's not the same as miniature ice ages and other things that have occurred in recent times. And what's different is the rate of change is so dramatic. It's so fast. And that's not the case with the geological periods over which changes have happened in the past, especially big ones. So the fact that you can see year on year changes in the temperature, and that goes up with very small errors cumulatively, is evidence that this definitely is related to human activity. What also people confuse is the fact that if there was no natural greenhouse effect, our planet would be so cold and we wouldn't be able to live here. So that's another idea out there, and it's also related to the ability of the atmosphere to retain heat. So those things get very confused, and we have to be very clear about which ones are the natural one that's already very significant, and then the one that we contribute to on top of that. And so that's another reason why people are confused. And I can remember also, as a professor of the States, being offered money by an oil company to sign papers that they would put my name on, which basically tried to prove that climate change was bunk, the papers were bunk. And of course I wouldn't do it, but I was offered money to do it, and I suspect that was quite a common thing back in the early 2000s. And it was quite shocking, really. But yeah,
a big question on how to mitigate the effects of climate change, or not the effects, to slow it down, is to switch our energy sources.
Yeah, that's
and
right.
A big one, obviously, is solar. So there's been a big push into solar energy, and of course, the sort of photovoltaic cells is the most sort of common, widespread, way of capturing solar energy. But the challenge, I suppose, is there's an efficiency issue. Where there's a limit to sort of the efficiency of those solar cells, you could say. So where are we in terms of the technology there? I mean, are we going to be able to exceed those limits, or is there some other technology that we can have a breakthrough in the solar area?
That's a great question. One of our big foci is on solar energy and what we can do to harness sunlight. So when you think about sunlight, it is the most beautiful and precious thing. It gives us life in the first place. And so one of the things that you would want to do is capture it and turn it into electricity. And so, as you know, when sunlight strikes a piece of, for example, silicon, from which we make silicon chips, the semiconductor industry's basis, the photons of light hit the silicon chip and they liberate electrons. And that becomes a current which we can then use in the same way that we use current that's coming from other sources of energy. So the basic idea is a slab of silicon, and that has been over many, many years studied and improved such that you could achieve efficiencies that are around the high 20% level. And that basic silicon was the thing for a long time, and then in the last 12 or 13 years, something like that, just over a decade, one of the ways to improve the silicon was to add a second material, a material that would absorb different color photons to the ones the silicon absorbs, which means you get more sunlight and therefore more electricity generated. And one of the materials that's very commonly used are called perovskites. And so perovskites are very easy to make into thin layers and add on top of the silicon. And so some of the sunlight will turn into electricity in the perovskite. So we'll go through the perovskite and go into the silicon where it will make more electricity. And in this way, you can make a so-called tandem cell. And in Oxford Photovoltaics, a company that was developed here, has been able to not just make them in the lab, which was the hard part, but which got the headlines originally, and it's now making them in a company that we have just outside Berlin, in Germany. And it's the first company that's producing them commercially. There are other companies trying to do the same thing. And
this is the perovskites.
Yeah, so that one is a tandem, that's silicon.
Okay.
Okay, one on top of the other. Now, that the fact that we're now able to make that commercially is very recent. It's this year. So that's already new and big as it is. But then there's a further piece of work that's been going on for a long time, and that's been in the shadow of this ability to make the standard sandwich of silicon and perovskite. And that is to make multi-junction cells, which are many layers of perovskite, but without the silicon. And these are different to the silicon solar cell in the sense silicon is 150 microns thick. And a human hair is maybe 20 microns thick or 30 microns thick. So that's quite thick. But now with these perovskite layers, they are 1 micron thick typically. And they're completely transparent. And you can put them on a foil, laminate them onto a foil, take them onto a foil, so that, and then you can take that and you can put it on the roof of the car. Or you can put it on your rucksack. And this means that we have new ways of locating the source of the energy. You put them there, so you can make transparent versions that you can put straight on your windows. They're on the sides of your house. And so this will completely change the limitation. One of the limitations of solar cells is that most of them are made of silicon until now, and the perovskites are just coming online commercially. And we have to have big spaces to make these. It's going to produce very large amounts of power. And so what we need is a massive amount of power to be able to make up for the fossil fuels. Because until we can provide low-cost alternatives to fossil fuels will continue. Because
and this new material that you talk about, this sort of very thin 1 micron thickness sort of layer, is that in industrial use now, or is it still in the lab? Is it how close is it to sort of production, so to speak?
So where we are now is that we are looking for a place to put a factory to make this. And the reason why our first factory is in Germany was because they made the best offer back in some years ago for the location of that factory. In other words, a local support. We're looking at a technology that is going to be quite game-changing. And in fact, we believe that eventually this technique is going to reach much higher efficiency too, maybe 45%. So where we are, it's going to be very efficient. It's going to be a lot cheaper to make. And we believe that, and it's easier to patent. And we believe that we should be able to drive price down for solar energy to about a third the price of fossil fuel generated energy. But now, when you've got something like that, then you want to be able to move to production as fast as possible. Now, because of the experience that Professor Photovoltaics have had over the years in Germany, as they learn how to work with perovskites and silicon for tandem cells, they're in a good position to be able to speed up the development this time, from in the lab to commercial. And so that commercial potential has already started to feed through. And people are very aware of it. And so what we now like to do is commercialize it. I mean, if you're a car manufacturing company, you've heard that now you could put something on the roof of the car and produce power. That gets you very excited indeed. And so what we've done is Henry Snaith is my colleague who's leading this, but many other very talented people, more than 40 in Oxford. And we've been looking at sites to start manufacturing. But at the moment, it looks like the focus of what would be a really fast growth new industry in the global green economy is not quite where the UK is thinking. They're thinking still about solar farms, which is very different to this. And unless there are going to be new incentives, we may not be able to locate the manufacturing in the UK, which will miss the opportunity to go with industry. So if anyone's listening to this, and there's anyone in government that can send the message that we've got this amazing material, it's a great breakthrough, and it would be possible to build an economy in the UK that could power cars. You could put it on drones. You could put it on your backpack. It could change the world, and it'd be fantastic. We'd have it start here, but we're open to business anywhere in the world.
I'm sure someone in the audience will take you up on that. Now on another energy source, nuclear fusion. Ever since I was young, nuclear fusion was always around the corner. You know, the idea that we can create the sun on Earth. You know, just these light elements, isotopes of hydrogen together and produce energy. But it just hasn't happened as far as I can tell. Correct me if I'm wrong, but where are we on nuclear fusion?
Well, so all of my life, we've been some years away, as you say. And I guess we are still some years away, but there have been some important developments that make us believe that we can be more definite about when things are going to happen than before. So it's a kind of consensus, really, from all the experts that, and within this field, there's not a consensus in everything, but in this thing, there is. Most of the experts agree that we're unlikely to be able to generate large-scale energy from nuclear fusion before around 2050. Now, that doesn't mean that the activities that we see today, including all the startup activities, not really, really important for getting to there. But it's a big difference between developing some extremely interesting techniques on a small scale and trying to produce something that is, as you say, making the sun and Earth, but making it in such a way that it's making significant enough energy to call it a power station. And so things that are getting better, we're making progress, but there's a long way to go. So I could go into a bit more detail about.
I guess the challenge has always been that the amount of energy you need to be able to smash these atoms together ends up being more than what you get out of it. So you have to somehow solve that equation, and the amount of the heat generated, and the plasma that's created causes all sorts of problems. How do you contain that? So you have to use magnetic fields and such, and all of this sounds incredibly expensive. So perhaps we can sort of start just from the, I don't know if it's an engineering sort of question or physics question, but like where are we on that kind of energy in, energy out,
right? So
managing the plasma?
You probably saw that the National Ignition Facility in the United States did some spectacular experiments about a year ago in which they did demonstrate more energy out than in. So that itself was a major milestone. Now, the main drawback with that is the National Ignition Facility was never built to develop nuclear fusion power plants. What it's concerned with is testing the stockpile of nuclear weapons. And how it works is by firing intense laser beams onto pellets of deuterium and tritium, two heavy isotopes of hydrogen, and raising the temperature in that small pellets that it produces a fusion process reversing time before it blows apart. So what that means is that it's not really designed to produce a continuous stream of power, because you've blown up the pellet. And then you have to put another one in and do the same thing again. You probably have to do that once every 10th of a second or even less. And so that while it was really important, it's not in itself how we're thinking that we would achieve fusion, at least in the near term. Right? So in the near term, the challenge is all about how you contain that plasma, which is at a very high temperature. And so the approach that has been the mainstreams ever since the original work by Sakharov and others in the Soviet Union in the 1940s and then into the 50s, where it became known to the world, was to make a magnetic bottle that contained the plasma, and that is called a tokamak. And these bottles, the shape of a donut. And the magnetic field in this bottle contains the plasma from coming out. But the problem is that it's not easy to contain the plasma. The plasma itself is at an incredibly high temperature, and its natural tendency is to try to escape the bottle. There's lots and lots of turbulence in the plasma, and this turbulence is a bit like flares from the sun, that kind of thing you could imagine. And so these flares from the sun, and also beams and particles that get produced in the plasma, like to go crashing into the wall of the tokamak. And when they do that, they unfortunately can just knock holes into it, so they can destroy it. So this becomes an enormous challenge. So what you have to understand is the physics of this plasma, and the better you understand the physics of the plasma, the more you can control the edge where the plasma and its enormous temperature and pressure are dropping to the ordinary temperatures and pressures of the room and the walls of the tokamak. And so over the last 10 years, some of the biggest developments have been in understanding the turbulence. And this is something where my colleagues in Oxford have played a leading role, along with colleagues at Princeton, MIT, and other places. And so that starts to, once you understand that, we're beginning to get to the point where you could imagine that you could see a path to developing fusion. But there's still a long way from doing that. But that's how it's seen. So there's several different types of boson that you can use to contain. One of those is the tokamak, but there's another version which has very complex magnets, coils that make electromagnets outside the region where you have the plasma, which is difficult to make. It's called a stellarator. But many people, it was also developed a very long time ago, and as a rival to the tokamak, but for a long time people thought it was too hard to make a stellarator. And more recently, there's been some significant success, for example, in Germany, where there's a stellarator. I forget the name of the town it's in, but that stellarator has produced some really impressive results over the last, since around the time it was built. And it's just been upgraded recently. And so that's an alternative way to perhaps build the tokamak, the iter, which is, iter is the Latin word for the way. And iter, which is a large, almost globally, tokamak, is immensely large and immensely complex to build because it's the first one on that scale. But, and that's expecting to be able to produce power around in the early 2040s. Now, that's slipped a lot. It's a very difficult project, but again, what we're going to look back on with ITER is not that it took so long to do, what we'll say that it was really important for the genesis of fusion. It's just a really hard project to crack, and so it takes a long time.
Yeah. Well, I mean, it sounds like the good news is that there's been huge advances in solar, which will come to fruition or are coming to fruition as we speak now and in the next few years. Nuclear fusion, we have a high level of confidence timing-wise, but it's a bit further out, 2040s, 2050s. But, there's been some positivity there. Now, I did want...
Yeah, and we'll get there. And when we get there, this will be playing an incredibly important role, because when we talk about net zero, what we're talking about is net zero for the current world, a world where most people on the planet live in energy-poor economies across Africa and other parts of the world that are less developed. And it would be not correct to not give everyone on the planet access to the incredible technologies of the modern society that we all enjoy in Western countries. And so fusion will play an immense role in enabling the world to use a lot of energy without causing heating of the atmosphere. And so I think it's a very important part of the equation. It's just coming online, like you say, a bit later But it's very, very important. And actually, all of these startups we know are working hard at the moment. People say, well, are they being realistic? What's going to happen is some of them will survive, some won't. But what will happen is they'll become an important part of the knowledge that we need to eventually make fusion possible. And some of them will become part of the pipeline, power supply line and development line that we need around the industry to actually make fusion in the future. There's many other things I could say here, but we should probably move to the next topic.
I mean, we've talked about like atoms. Let's go below that to subatomic levels of quantum. And quantum computing has been it's captured the imagination of many people for many years now. There's lots of startups around this all. It sounds really quite compelling, the idea of quantum computing. Maybe for the benefit of our audience and even for myself, it might be useful for you to, as simply as possible, if you can, explain what quantum computing is compared to, say, classical computing, and then we can go from there.
Okay, that's certainly a good place to start. So the first thing to keep in mind is what is an ordinary computer? So an ordinary computer has bits that store the information. You can turn them on or off like a switch. And these bits are ones and zeros. And that enable you to represent numbers in binary form. And the more bits you have, the more numbers you can represent. And that's an ordinary computer. And when you get a quantum computer, the difference is that you still have bits. These bits are quite different in how they're made to the bits in an ordinary computer. And we come on to how they're made in a minute, and there are many ways you can make them. But the main thing that they all have in common is that they still store ones and zeros. But the difference is that they don't store a 1 or a 0 like an ordinary computer. They can store the 1 and the 0 simultaneously. In fact, that's their nature. And what this means is that they can perform calculations exponentially faster. It's a bit like the difference between in a traditional computer, you go into a library like the ones in Oxford with some incredible number of millions and millions of books. And with an ordinary computer, you work your way through the books. But with a quantum computer, you can read all the books at the same time.
And the kind of the quantum theory underpinning this is superposition.
That's right.
The ones and zeros at the same time, and entanglement, where the quantum kind of are connected or correlated together, and which just expands the amount of information in the system, I suppose.
That's right.
And this is also, quantum mechanics just sounds really sci-fi and spooky, and as they've sort of said in the past, this idea of entanglement and superposition. But that's central to how quantum computing works.
That's right, exactly. So you would like me to say something for the listener about what these things are: superposition and entanglement. Would that be of interest?
Yes, of course. Yeah.
Yeah. So superposition is the ability of a quantum system. Can be a qubit. It can be something else that is governed by quantum. An atom is governed by quantum mechanics too. To be in multiple states at the same time. In the case of the qubit, that's the 1 and the 0. Now, the superposition itself is a difficult thing to understand, but it's an essential principle of quantum mechanics, and so it's often illustrated by an experiment that was actually conducted a long time ago, 1801, by a guy called Thomas Young, who was a physicist in England. And the experiment was called the double-slit experiment. And what it was originally intended to do was try to explain why a particle can be a particle, but also be a wave. And that's deeply connected to the concept of what superposition is. So when the experiment is used today, it's used to understand the way electrons connect like waves and create interference, which is evidence of the superposition. So what happens is you take a beam of light and you aim it at a barrier, and this barrier has got 2 vertical slits in it. And the light passes through the slits, and the resulting pattern is recorded on a photographic plate. And when one slit is covered so that the light can't go through, then the pattern is what you would expect to see. In other words, there's a single white line on the screen. And that line depends on which slit is open. But it would always line up with that slit, just as you would expect. So intuitively, one would expect that if both slits are open, the pattern of light would be two lines on the screen. But I think you may have done this experiment once if you were studying it in physics. In fact, what happens is that the photographic plate separates into multiple lines, lights and darkness and varying degrees, an incredibly beautiful pattern. And what is being illustrated by this result is that the interference is taking place between the waves, through the slits, in what seemingly should be two not crossing trajectories. But somehow or other, it's found all the ways possible. The light has found all the ways possible to get to that screen. And so, in order to see how this might possibly occur, other experiments have focused on tracking the paths of the individual photons. And surprisingly, the measurement in some ways disrupts the photon's trajectory, which is a very fundamental thing about quantum mechanics, but not just quantum mechanics. When you observe something, you affect it and you disrupt it. So surprisingly, the measurements that you've now disrupted mean that what you get is what would be predicted by classical physics. If you disrupt one of the photons, then you're only going to get the two slits again. And this is a truly remarkable thing. And this has led scientists to conclude that superposition, which is this effect, this building, which is what we see as interference, cannot be directly observed. But what you can only observe as a resulting consequence, the interference itself. So now in computing, the concept of superposition has important implications for the way information is going to be processed and stored. For example, today's classical computers process information in bits and ones and zeros, but now with the computer, the quantum computers of tomorrow, they store in these qubits, these superpositions of two states. So this is the idea of superposition. And then entanglement is the next bit. So entanglement is something that often is described as kind of a spooky action at a distance. But this is a highly misleading way to think about it. Although it's natural to think about it that way, Einstein did after all. So entanglement is a kind of correlation, but it's very deep and intrinsic to the nature of the world, the nature of the universe. It's something that connects things, even if they are millions of miles apart. Once they have that connection, you can take them and you can move them apart and they'll still have that connection. And which is why some people think it's very strange and very unusual. So this entanglement can be best described by a simple example. If you imagine flipping a coin, seeing it come up heads, but knowing for sure that a second coin in your pocket would also come up heads based on that result, you'd say that's pretty amazing. It's not intuitive, but it actually is what really happens in quantum mechanics. And so how does it come about? So the way it comes about is we describe quantum particles by what is known as a wave function. And we can think of the wave function as a bit like a library. And that library is full of all the possible states that the particle could be in, or a pair of particles could be in, or even three particles or more. There's one wave function. And when we observe the particle, its wave function collapses, it's destroyed. Not the particles, but the way in which the wave function describes the system of particles is destroyed. And we observe it to be in one of the states at random. So either the coin is up or it's down. And we'll see that. But if we flipped a quantum coin, we'd collapse its wave function onto either heads or tails. So if you now have so that's a coin. If you have an entangled pair of coins, however, the two-coin wave function is a mixture of those two individual coins, up and down, or heads and tails for both of them. And if you flip one coin and it collapses, the entire wave function collapses too, which fixes the result of a flip of the other coin. So, say we prepared our entangled coin pair such as always produced, such as a heads and a tail, where both coins are flipped. So it's always one head and one tail. If we flip the first coin, it comes up heads, we know for sure the other coin will come up tails. And that happens. That really does happen in the world. It's not too weird. It's just that we have to accept the reality of the wave function. And so we can't consider the two coins as separate. They're not separate. They're described by this wave function.
Okay, understood. And so if we bring this back to quantum computers, so quantum computers use this idea of superposition entanglement, and that
Yeah.
allows for so much more information to be in the quantum system.
Yeah.
The challenge for quantum computers, though, are how do you extract information out of that into the classical world which we live in, while somehow getting that information out. And that I suppose is the paradox, that there's a lot of information and there's a lot inside the quantum system, but you need to somehow translate it to the classical world, which is what we live in, to be able to understand the output. So there's a sort of translation issue. And I suppose the other issue is the quantum state is very sensitive, and so it decoheres very easily. So keeping it in the quantum state is a big challenge.
That's right. That's the coherence and decoherence, in fact. So the way in which it may be best to think about this is to say, what is it we need? What do we need to make a quantum computer? I mean, and also to say at the same time that quantum computers are not going to be something that replace ordinary computers. They are for special tasks, difficult tasks that we can't do in other ways. And in some cases, a high-performance computer would be able to do the task in others. And what is also clear is that we're not going to have quantum-enabled iPhones anytime soon. So one day maybe all these things will be possible in the future, and in a future in which quantum revolution too changes everything about the modern technological world. That's still very, very far apart. The best known example of the quantum technology is always turned out in the quantum computer, that it's one part of a much bigger universe of things, including quantum sensing, quantum metrology, and so on. So there's a guy called DiVincenzo, and he outlined 5 criteria for a quantum information processor, in other words, a quantum computer. And these criteria have been used as a basis for assessing different possible physical implementations of a quantum computer, because there's lots of implementations. So what they are, one, that you need a physical system containing 2 well-defined levels in a quantum system. So it needs to be quantum, and it needs to have 2 levels to it, which mean 2 different energy levels, such that you can store the 1 and the 0 in some way. There can be a difference. So you have to have a basic system like that. And there are many examples of this, but 2 of the best known ones are ion trap quantum computing, which uses an ion. So that's a charged atom. At the different levels of the electron, or electrons going around the atom, enable it to store the 1 or the 0. And there's also another approach using a technique from microelectronics fabrication tradition, which is to make a superconducting loop of material. And these 2 are the best known. In any case, but there are many other implementations as well. So what you need then is a system that can hold a 1 or a 0. Then what you need next is the ability to initialize that system into a well-defined determinate state. In other words, if you want it to be a 1, it's got to be a system where you can tell it you are a 1 now, and you're going to be a 1, and hopefully stay like a 1 for a long time until we tell you not to be a 1. And then the third thing is that this qubit, we'll call it a qubit because that's just a general name for it, that it needs to have a thing called a decoherence time. So that's how long before it ceases to be a 1 on its own, just because of something in the environment, for example, that has affected it. And that needs to be longer than the gate time. The gate time is the operations you want to perform on the qubit, in the same way that you perform change 1s and 0s in an ordinary computer. Because if that is not the case, you'd have lost the information before you've had time to operate.
Okay, you won't have time to do the calculations,
exactly,
the logic gates or times, whatever.
Right, exactly. And then the next one is you need to be able to make a set of basic quantum gates, which can be applied to the qubit or a pair of qubits. And you need to be able to do that with accuracy. Because otherwise, even if your qubit is along decoherence time, if you can't actually manipulate them in such a way that you can do the various logical gates that you have in a typical computer, then you can't actually make any calculation in the first place. And then the last one is the ability to read out the qubit once it's done your operations on it in a reliable way with high accuracy. And so the different platforms that exist have different performance levels for each of these 5 criteria. And it turns out that at the moment, the trapped ion has the best performance in these 5 criteria, which itself is interesting. And we're very pleased to say that at Oxford we have one of the leading trapped ion groups in the world. There are other leading ones at NIST, in Vienna, and other places. And we also have a very exciting company called Oxford Ionics that's seeking to build useful quantum computers based on ions. So that gives you a bit of an example.
And you said at the start of our section on quantum computing that quantum computing won't necessarily replace all the functions of classical computers. That there's that they have specific use cases or maybe orthogonal to classical computing. What are some of the use cases for quantum computing that experts believe are viable?
Yeah. So when people think about quantum computing in general, one of the things that comes up right away is why are they so important? Why are they so actually disruptive? And the reason why they're disruptive is because they challenge security. There's a real security threat if you have a quantum computer and someone else doesn't. Quantum computers can crack even the most advanced security measures faster, a lot faster than classical computers. This is why why every country needs to have their own quantum computers, most encryption keys that protect sensitive data, including on government servers. Fortune 500 companies rely on hard mathematics. It simply takes too long for humans or classical computers to do the math to reveal the encryption. And that's how the encryption keys work. And how long would it take? Thousands of years. But that's with ordinary computers. And then with a quantum computer, you can perform these calculations in minutes in principle. So quantum computers would change the landscape of data security. And companies are working, of course, now and have been for some time on quantum-safe algorithms to defend against quantum threats. So that is the one whole area in which quantum computing becomes a major part of the future. There's other areas as well. The second one is that there's business value in quantum computing. Even at an early stage, it's going to revolutionize industries like finance, pharmaceuticals, simulation, artificial intelligence combined with quantum computing, automotive industry over the next few years. It's because, for example, with quantum computing, you could do simulations of complex chemical reactions, including designing new materials and designing new drugs in a way that's much more efficient than before. And so all big pharma needs to have this capability. Otherwise, they will lose their preeminence, their market share. So
and when do you think quantum computers will be able to be used by industry? I mean, are we talking 5 years away, 20 years away?
So it's getting much, much closer all the time, because what's coming out, what you can go on the cloud right now and you can use a quantum computer is just not a very good one compared to what will be available one day. But it's all happening all around us right now. And I think within a decade at most, we should be there. Some people will tell you, if you actually talk to people developing the quantum computers, in general, they tend to be quite optimistic. And there's good reasons, because a lot of exciting stuff is happening. But whether it's 5 years away or whether it's 10 years away, but that's the kind of it. There's a lot coming on now with far from perfect quantum computers, and that will gradually be a trend. And gradually they'll become more reliable, more capable, until eventually they become very general purpose and general use. But you won't have a quantum computer in your own home, right? Because they're very complicated pieces of kit. You need the low temperatures. You need all kinds of shielding from the environment. We can't have them in our own home, but what you will have is access to quantum computing on the cloud, right? And big companies like Amazon Web Services, IBM, and others have quantum computers on the cloud now. There's an Oxford physics department spin out, Oxford Ionics, that had a quantum computer on the web recently, and it was one of the most performant while it was there. I don't know the current status, so I haven't had a chance to look. And then the whole business of how do you program a quantum computer? The world needs to be trained in that, and that's what's being provided by these cloud services now that have real hardware that you can access, and you can learn how to write algorithms. And then put them on the quantum computer. And so there's a gradual phase. It's not going to be an abrupt change. It's a gradual change that's happening, I think. Eventually we'll get to the point where the real phase change. We say now it can really do the things we promised it could do. Now, we haven't got to that point yet, but we're working our way up towards it, like getting to the edge of the waterfall, and then suddenly over we go, and it's the world, and quantum computing becomes normal. But it doesn't replace ordinary computers, because ordinary computers are fabulous things, many, many things indeed. And in fact, you can combine high-performance computers and quantum computers together to achieve more things in some cases than you could otherwise do. So it's an incredibly exciting time for quantum computation.
Yes.
And it's very exciting to be in Oxford, because we're very much at the heart of that, which is an incredible privilege to be in.
We've covered a lot of science, and I just wanted to come back to Oxford. And I understand that Oxford's launched an initiative to help educate students outside of the university system. Can you tell me a bit more about that? That sounded quite intriguing.
We're very proud of that. So what we realized some time ago was that we have something very special in Oxford because of our tutorial system. You know, this is the idea of teaching in small groups. So even though students have the opportunity to go to lectures, they also have the requirement to learn physics in small groups with world experts in physics. And this is very much the idea of the apprentice and the master. And it's a very personal relationship. And you get to know your tutors over a number of years, and they have been trained over many years to nurture your love and your passion for physics and help you become the master craftsman in physics. In other words, physics, as you know, it's not about remembering things. It's about intuition and learning how to look at the world in a new way and using that intuition to solve all kinds of problems, some of which are nothing to do with physics and many of which are. And so we want young people to have that experience already when they're in high school. So, of course, the school cannot provide that experience in general because there's many students to instruct. Secondly, they have very little time each week to study physics and to study mathematics. And also there's a very large shortage of physics teachers. I mean, when I was a kid at school, we didn't have a trained physics teacher. We had a person that did a good job with us, but he was not a trained person in teaching physics. And today in Britain, there's still a big shortage of physics teachers. And so the idea was to try to give that experience of our system of teaching to kids from around the country. And so we created a new program called COMPOS, the Comprehensive Oxford Mathematics and Physics Online School. And it was launched 4 years ago. And in that time, over 90% of the students that have taken it, and they're from across the country. You can be at any type of school. You apply to the program. You get a letter from your science teachers saying that you are seriously excited about science. And if you're admitted, then we have very large number of applications, and we'd like to have the resources to have more. It's all funded by private donations at the moment. So if you're admitted, what happens to you is that you will, after an aptitude test to make sure that you do well in the subject, then you would experience first some online lectures that talk about themes and ideas in physics that go beyond the national curriculum with a baseline. And then you're sent problem sets online, which you work on, and then you send them back to your tutors. The tutors are students from Oxford, either graduates or undergraduates, and sometimes tutors from other universities. We have so many students now that we need a lot of tutors, and we pay those students. But those students learn to teach, and that's in itself a very valuable benefit for them. But the young people taking the course, they work through the problems, they send them back to their tutors, the tutors mark them, and then they meet online to discuss the problems, just like you would do in a tutorial in Oxford. And this runs throughout the year. And what has happened is over 90% of the students have reported greater confidence in science, as you would expect. And 85% say that they're likely to go on to university, and they weren't necessarily going to do that before they took the course. But what I find particularly remarkable is that now that we're running for this length of time, the students that completed the A-levels in 2023, 100% of them went on to do a STEM degree. This is truly astonishing. 96% at Russell Group institutions, with 50% of all the students going to Cambridge or Oxford, which is a breathtaking
quite remarkable.
for these young people. It is. And we are so proud of what is being accomplished. The mastermind behind this is my good colleague, Alex Zabowski, who is an expert in quantum information and quantum physics. And so the statistics go on. The average compost student outperforms at A-level by 55% in maths and 48% in physics. Well, the top performing compost students with an average GCSE score of 9 achieve 100% A-star in physics and 93% A-star in math. So you see why so many of them go on to a strong university. And so it's an exceptionally exciting program. And what we want to do now is continue to grow it and give more people the opportunity to experience it. And there's no reason why other universities couldn't emulate us and do the same thing to provide even more support for young kids growing up in the UK and ultimately in other countries too. It works in any language because physics is truly universal. And so we're very, very excited about this program. I think it can make a massive difference to the ability to prepare the UK and other countries to be a real natural location for discovery and development and to create an advanced workforce that can enable the potential for things like quantum revolution too, that will change the quality of life for everybody on the planet in time. So there's a massive amount of stake, starting locally and growing from there. So we're incredibly excited about it.
Absolutely. Now, I did want to ask one or two personal questions. One was actually, it just came to my mind when you were talking about this initiative, which is in your career as a physicist, obviously you've been successful in many different aspects, in terms of, breakthroughs, cutting edge and so on. What are some of the elements of that you think have helped you, be a successful scientist? You mentioned intuition, for example. I mean, what are the elements that you think are important?
I think probably the biggest one is not knowing things. Because when you know things, you often imagine that either there's nothing left to know, or else you think that anything that's left to know is too difficult to know, and so you might give up. And I found in my career that I got into new areas, not knowing they would be difficult, and then in making things and doing science with them that everyone thought couldn't be done. But it turned out that it's not sure that it could be done. It was just that maybe they were thinking about it the wrong way.
One more question I had, which was about books. I like reading books. Were there any books that really influenced you over your career?
Yeah, I should say that as a person that, like you, very busy, and we don't have too much time to read books, because I do like to read them. So there have been a couple of books I thought about in answer to this question. It's a book I read when I was about 10 or 11 years old, and it's called Starlight Nights. And then it's got a subtitle, The Adventures of a Stargazer. And at the time I read the book, the first part of the book is about a man called Leslie Peltier, and he grew up in the Midwest of the United States, in Ohio. At that time, when I was 10 or 11 or 12, I had no idea where Ohio was. But what this was about was this young boy who wanted to see the night sky and love the night sky. And so he spent all his free time doing that and learning. He had a small telescope and a passion to observe and understand the universe, and did all this in a background where there was not really support for that, a rural community, not a lot of interest in the subject, with everyone admired the night sky. And it tells that story in Ohio in the early decades of the 20th century. And then as the book goes on, it tells the story of how he grows up and he becomes one of the most successful amateur astronomers of the 20th century. He was a hunter of comets and nova and things like that. And I found that very inspirational. And so what I took out of that and what I take out of that today is an encouragement. I use it in examples when I'm talking to students who are going off from an education in Oxford. I use it as an example, both of young people and their families and any other young person, to read a book like that, to be inspired by your dreams and your passion, and then use the knowledge that you have to understand the world and help make the world a better place. And so that's the kind of
That's
message.
great. I mean, I'll make sure to read. Yeah, I'll make sure to read.
I recommend it. It's a very, I read it twice. It was the only book I think I ever read twice. The first time when I was 11, 12, something like that. And the second time about 4 years later. And it was inspirational both times.
Yeah. And then finally, what's the best way for people to reach out to you or to the department if they were interested in supporting, learning more about what the department's doing, but also supporting some of these initiatives that you talked about, whether it was the education
Absolutely. So it's through the physics department website.
Solar tech.
It's through the physics department website. It can be reached through that.
Great.
And we do need people to, we'd love to hear from people in your audience, because with Compass, for example, it's not an expensive program to run, but we simply are relying on donors. And with more donors, we can give more young people an opportunity to become numerate, really numerate, in a way that means intuition in beautiful mathematics and beautiful physics, and truly love those subjects and give the gift of their love also ultimately to the development of humankind. And so every person can help us with that. And we definitely do need some more resource, because we're right on the edge. We've not been able to run the program this year. We've been struggling. Hard to believe when it's such a great program. But the word's only just getting out. That's why. I mean, I'm not a chance to advertise it. This is one of the first times we've been able to talk to a broader audience. And so it's very exciting. It will make a big difference, but also about all the technologies. And South we talked about today. I'd be very happy to communicate with any one of your readers, and going through our website is the best way to do that.
Okay, great, Ian. Thanks for that. It's fantastic. I learned a huge amount. I think I understood most of it as well, thankfully. And so, keep up the good work, and look forward to staying in touch.
Absolutely. We're going to have an opportunity to meet outside of this interview when you come back to Oxford at some point. And I can show you some of the new things that we have here now.
Absolutely. Thanks for listening to the episode. Please subscribe to the podcast show on Apple, Spotify, or wherever you listen to podcasts. Leave a 5-star rating, a nice comment, and let other people know about the show. We'd be super grateful. Finally, sign up for our free newsletter at macrohive.com/free. That's macrohive.com/free. We'll be back soon, so tune in then.